what's called classical planning. Classical planning, I mentioned just before we had the break, that a lot of planning can be thought of as search in different types of models. And classical planning is one of the most widely used models for describing actions for robots and other autonomous systems. And it was invented as part of the Shaky project, which I demonstrated earlier. So that's this robot here, which is able to push blocks around and do very limited interactions. But this was in 1966. It was an amazing piece of work at the time. So classical planning is a model for planning problems. So there are algorithms as well, but the most important thing to take from this is the model, the way the world is described. So classical planning has two things that make it unique. One is that it uses a factored representation. So a factored representation describes the state as a collection of independent variables. So we can think about a world state as a collection of variables, exactly like we did in the first lecture. So we'll give an example of that. And then the key kind of part of the model really is that it has an action representation that uses a subset of first order logic, or alternatively it uses something called set semantics, which allows people writing these planning models to express a wide range of successor states using a compact representation. So this is a way of describing how to build a tree, but doing so without having to enumerate all of your states. So typically, planning problems have hundreds of thousands or even millions of states. And we want to be able to write down what those states are without writing down every single one. We want to write down a recipe for creating states and trees. And you can think of the classic planning model as a recipe for describing those trees compactly. So we've already seen a classical planning problem. Here we have this factored representation at the top, right? We've got, sorry, starting my iPad again. We've got this factored representation. We've got this collection of variables, and we've had these action models that we didn't really expand, but this is the kind of way of thinking about it. We've got different variables that can take values, and we're going to have actions like drive and load that we can use to change these variables. So classical planning makes some assumptions. We haven't really talked about these, but it's useful just to get a sense of what they are. So classical planning is a problem which is called fully observable. And fully observable means that our planning agent always knows the complete state of the world. So you can imagine that this is a case where the robot looks around it and always can see and write down everything accurately. So it's actually quite rare for a planning problem for a robot to be fully observable, but it's typically an assumption we make. And we make that assumption because we build abstractions of the world. And when we go to those abstractions, the worlds are typically fully observable. That's how we choose our abstractions even. So this is deterministic, and I used that word in passing previously. That means when the robot performs an action, the outcome of that action is fully determined by the previous state and the action itself. So that means we always know what state we're going to end up in when we apply an action. Machine vision is not deterministic or fully observable. So whilst you might want to think, so Peter in the chat said machine vision, which I assume related to kind of fully observable worlds. In fact, typical machine learning algorithms are not so reliable as to assume that they give you full observability. Classical planning also assumes, and actually everything we've seen so far, assumes that the world is static or the environment is static. So importantly, this means that our planning agent is the only agent that changes the world. And the world only changes when the planning agent decides to change the world. Okay, this is a static environment. It's quite a limiting assumption. Again, if you put a robot into an office or a restaurant, the world is not static. And we also, again, assume that there is only one agent in the world that's planning, which is our planning agent. So these are a kind of set of problems that make planning, in some sense, very easy. But it hasn't stopped planning and classical planning work from being very popular and being used quite widely in the history of AI. And I think that's largely because when we build our planning models, whether it's for robots or cars or anything like that, we typically build abstractions of the world. So we build models that actually obey these properties quite easily. It's only when the robot worlds get a lot more challenging that these things no longer become true.